Farshid Hajir. Our speaker is Farshid Hajir from University of Massachusetts at Amherst. And he speaks about asymptotically good families of fields and curves. So please, Farshid.
Thank you very much. I want to thank all the organizers for putting this meeting together and persevering despite the conditions of the pandemic to bring us all together. I have a particular apology to make to everyone that I have not been able to attend any of the talks live until just the previous talk by Beelan. And I have a full-time administrative job and just have meetings all day long. There just wasn't any way I could do it. But I've been watching the videos, as many as I can, and hope to be able to stay for a few more talks today. I'm talking about asymptotically good families, and when the organizers wrote to me, they asked me to talk about class field towers and their relation to counting points as a way to see if there are some ideas that can be used for cross-fertilization. And so I was particularly amused to see the video of Sayer, which was one of the best interviews with Sayer I've seen, by the way. Christophe and also Lisa, you should be proud of it. And he started the interview by saying that this whole genesis of his Harvard course was started with Golod-Shafarevich and the connection to discriminant bounds, which is where I started my first steps as a mathematician when I was a student at MIT working with Harold Stark and later on also with Dick Gross. And my very first semester in fall of 1988, Sayer was at Harvard giving a course on Galois groups. And so I attended the talks and I understood practically nothing and loved every minute of it. So 2 years later, he was back at Harvard and I cornered him to ask him a question about class field towers and Golod-Shafarevich. And if you've been at Harvard and you know the environment there are all these little alcoves where there's blackboards and you can talk. So we went into one of those alcoves and he started to write on the board to answer my question. And I started to take notes and he said, no. There is no notes. We don't take notes. This is just off the cuff. So I put my notebook away and here I have to confess to Sayer, je vous ai trahi. I went back afterwards and I wrote down what was on the board. And it was a really good thing that I did because as I went on thinking about these questions, he had told me I should read Lazare. And I had forgotten that. And then later on, as I learned more, I came around to, I should read Lazare. And that led me to all kinds of things that I was able to understand. So I have a lot of appreciation for Sayer's visit to Harvard. So Sayer describes how in the 80s, he was looking at this paper by Manin from 1981. What is the maximum number of points on a curve over F2, or something like that. And as he was playing with this question, he remembered that he used to have a pen pal named Hendrik Lenstra that he used to write letters to, and they would exchange like a contest to find examples of number fields of small discriminant and particular degrees. And as he was trying to find curves with specified number of points, he had this realization that actually these two games, as I'm sure you could hear Sarah's voice saying it, these two games are very similar. And it's not just a similarity, there's actually a lot going on there in that finding a curve over a finite field with a lot of points, like if someone says, I have a curve over F5 with 1,000,000 points, you're probably going to be impressed, but you may not be as impressed if you ask them what the genus is for the curve, right? So if it's large as compared to the genus, it's a similar game to if you find a number field whose discriminant is small And what do you mean by small? Well, compared to the degree. So this is the source of the analogy that I'll be talking about. So one way of playing this game is to seek specific gems, I call them, like really a beautiful little object that, um, uh, well, it seems beautiful if you've been hunting for it for a long time and you find it eventually. So let's say you're looking over F13 for curves of genus 2 having 26 points. And here I was thinking most people in this audience probably know, oh yeah, I know that exists. And the other half are thinking, oh, I can go to manypoints.org, which I just learned about from this conference. And there it is. And in fact, so this achieves the maximal number of points there. And there's a similar flavor if you ask, is there a number field of degree 17 that has a unique real place and has discriminant 14,947 to the 8th? These are the types of questions I asked myself around the time that I was going to ask questions from Sayre. And so in this case, yeah, we know such a field exists. And that's because the quadratic field with discriminant negative 14,947 has class number 17. So its Hilbert class field has a subfield of index 2, which you get by adjoining the J invariant of an elliptic curve with CM by this field. Although if you want to compute the minimal polynomial of that J invariant, it'll be much more expensive than the polynomial I wrote down here, which I found in Paris. And Paris, by the way, computes this using elliptic units, which is a much more efficient way of doing things. And this kind of computation is actually what my thesis turned out to be about. So that's one version of the game is, pick a genus and pick a finite field and look for curve with lots of points. Or find a specific number field of small discriminant given its signature. So another version of the game, you don't look for a particular gem, but you look for a whole infinite family that you hang on a necklace, say. And so this way you're looking at the asymptotics of families of curves. So you're looking at the contour of the shape of such bounds that you could get. And I always thought it was interesting that Sayre was interested in both versions of this game. And in fact, I think in his video, if I remember right, he would say, on Tuesdays, we would do specific curves. On Thursdays, we would look at asymptotic results. And in this talk, I'll be talking about asymptotic questions. So about, the Ihara function A of Q, which, is a major star of this conference. And for number fields, the analog of that is the Martinet function, which may not be as well known for many members of this group, but it's analogous. And in order to talk about both of these things at the same time, I'm going to introduce a little bit of formal machinery, which is not very meaningful in itself, but it's just a vehicle for me to try to highlight the correspondences between number fields and function fields in this case, or number fields and curves. But I'm also going to use the opportunity to talk about another context of graphs to show that the same kind of phenomenon happens in other places, and there may be more lessons to be learned from doing further comparisons with other types of algebraic objects. And you could do the same kind of thing for codes. But I didn't think I would have enough time to talk about that. And here I wanted to mention also that there's a paper by Andre Weil where he talks about analogies in mathematics, and I think it's a letter that he wrote to his sister Simone. And it's a really beautiful piece of writing. And I always connected to it because I found that using analogies to make discoveries is some of the most enjoyable work that a mathematician can engage in. And especially trying to figure out certain things are different. Um, like, for instance, if you recall, if I go back to it, the way it's natural to think about it is to fix a genus and then try to maximize points. But when you think about number fields, it's really in the reverse order. You fix a degree and then you try to minimize a discriminant. And you don't say to yourself, okay, discriminant 14,947 to the eighth. What is the highest degree field that I can find with that discriminant? I mean, it's a perfectly equivalent way of looking at it, but it's very odd to think in those terms. And sometimes I've tried to do that, but I always end up coming back to what feels natural. So let me introduce this abstract nonsense, just a formality that I don't think it's very useful, but it's a way to unify multiple different situations. So let's say that a context is a quadruple where O is a set of objects or isomorphism classes of objects. T is a parameter space of types of objects. Tau is a function from objects to types. It just says, what the type of the object is. And alpha is the critical function here. It measures the quality of each object. So, and of course, I use the word quality to indicate that the higher alpha is, the better the object is, the more valuable and the more rare and harder to find. So something that I was calling a gem would have a higher quality. And by the way, in the case of codes, it's much better not to have the quality as being a one variable, take one value, but to have it take values inside the unit square, 0, 1 cross 0, 1, because you can map it to both the minimal distance and also the rate of the code, the relative distance. So let's try to make this a little more concrete, this abstract. I'll just want to give you an example of the curves over finite fields. I'll use the equivalent language of function fields because that's more analogous to number fields. So I'm going to say that the set of objects is just function fields. So finite extensions of the function field of P1. And the types are just the prime power. The set of types is the set of all prime powers. So basically, I'm taking a function field over a finite field, and the type of it is just the cardinality of the finite field. And finally, what is this measure of equality? This is something that will be familiar to everyone here, is that you take the number of degree 1 primes of the function field divided by the genus, or if you think of the curve associated to the field, you're just counting the number of points on the curve, dividing it by the genus. So, okay. So what do you do when you have such a situation, such a, objects of a certain type and having a measure of quality? Well, now you can look at families. So a family is a sequence of distinct elements of objects. And I say the family is isotypic of type T if they're all of the same type. So we usually don't go comparing curves over F2, over F7, etc. We keep the type the same. And we extend the notion of quality, the alpha, from individual objects to the family by taking the lim_inf of the sequence of qualities of the objects. And then I stole the phrase asymptotically good from Spassman and Ladut's paper. It's a great paper I like to mention all the time because it has so much information in it, and treats global fields on the same playing field, which is the spirit of this talk. It appeared in the Moscow Math Journal. I forget the year now. But we say that the family is asymptotically good if the quality of the family is positive. So notice that if I go with the analogy of a necklace of gems, I'm being pretty stringent on a high quality necklace. It can have one or two gems that are not very valuable, but asymptotically speaking, if I ignore any finite number of gems, I still have a non-zero lower bound for a subsequence that stays high quality. So it's typically hard to find these asymptotically good families. And I think Bilin was just mentioning that, usually you try and you fail. So, but when you do find them, the questions are, how large can the quality of an asymptotically good family be, as measured against by the, again, always by the type? And can we find, basically, can we find upper bounds for them? And can we create examples that have very high quality? So let's just review. What does it mean for a family of curves to be asymptotically good? Well, it means that the number of points grows linearly with the genus. And one way to do that, and this is where Sayre ended up, in his Harvard lecture notes, was that if you have a tower and you begin at the base with a non-empty subset of the points of degree 1. So if you have at least one point of degree 1, which splits completely, then you're going to have the genus growing linearly with degree. And so, a really good case of that, which actually predated a lot of these, was the tower of modular curves, but over FP squared, so that the super singular primes are there for you to play with, satisfy these criteria, and so they give you asymptotically good families of curves. So people know that they should just interrupt if there are questions, right? I assume that's a standard norm. So back to the general context, general theory of, what if we had interesting objects we were looking at? What do we do? How do we measure their goodness? Well, we define what I call the asymptotic envelope, which now becomes a function from the set of types to non-zero real numbers in the following way. You just look at all isotypic families of type T, and you take the supremum over the qualities of those families. So I hope this is clear. So it's a soup of a lim int basically over the families. And so if you think about what that means, that, for the case of curves over finite fields, it's just going to be exactly the Ihara function. We'll see that in a second. And that the game here is to try to determine this asymptotic envelope A of t. And typically what happens is you get an upper bound and you get a lower bound, and you work like as hard as you can to make those as close to each other as possible so that if you're lucky, they match up. Now, one observation is that the upper bound, almost always in all the cases that I know, the upper bound comes from some kind of zeta function and some kind of Riemann hypothesis being applied to that zeta function, giving you the best possible information. And as Sayre was saying in his interview, he said, morally speaking, I am a student of V. So if there's some bound of V, I don't like the bound to be not sharp. You know, it should be sharp. So I am a student of Stark. And so in the same way, I like these upper bounds always that come from, in the discriminant case, which come from the Stark method of using explicit formulas of V to be sharp. So I'll talk about that a little bit later. Now, on the other hand, the lower bounds, they obviously come from examples. If you can create one good asymptotically good family, that immediately gives you a lower bound for the asymptotic function a of the envelope function a of t for that value of t. And so it's not surprising that automorphic forms are involved in those in the creation of the lower bounds, because it, they're objects with lots of symmetries. And so the way I think of it is that the symmetries cause, as soon as you have like one point, let's say one there's one area in your object that's good, the symmetries cause there to be lots more of them. So now let's go back to curves over finite fields. Here I've set things up exactly so that the asymptotic envelope function is just the Ihara function a of q that everybody loves. And so we know if we just apply V, we get the bound that a of q is at most 2 times the square root of q. And that comes from Riemann hypothesis applied to just one curve. But Drenfeld and Ladutz realized they could apply it to more coverings of it, and that's how they get that it's bounded by square root of q minus 1. They save a factor of a half, and then they subtract 1 for good measure. And that turns out to be actually because of the example of modular curves, which I think existed earlier. So Schwarzman knows the history of all of these really well, so I would defer to him. But I think it turned out that the a of p squared being bigger than or equal to p minus 1 was known before Drenfeld and Ladutz. But in any case, we know that for half the cases that we've determined what a of q is, it's exactly square root of q minus 1. But of course, what happens for a of p, this is still a big mystery. I haven't been able to keep up with everything, but as far as I know, a of p is bigger than c log p is still the best that's known in general for all p. And this was done by Sayre in his notes using class field towers. But I want to note also that he had to use a little bit of graph theory to optimize the conditions to get this bound. It was a non-trivial piece of trickery. Although I think maybe others have found other ways to get around it. But I still think it's remarkable that between log p and root p minus 1, there's a very big gap. And I don't know how people feel about this, but I'm not so sure that square root of p minus 1 ought to be the right answer for prime fields. And I'm looking at the list of people I can see to see which way their heads are nodding. But so Schwarzman says no. Okay, that's good. So now let's go to number fields. So consider a number field of degree n and discriminant d. Then the absolute value of d to the 1 over n, the nth root of the discriminant, is called the root discriminant. And the important thing here to know is that the root discriminant remains constant in an unramified extension. And another way to think about it is that the log of the discriminant is or 1/2 the log of the discriminant acts like the genus for a curve. That's a pretty good analogy. So the set of objects are algebraic number fields. And the type of a number field here is R1 divided by n. So R1 is the number of real embeddings of the number field. And R1 divided by n is, Faltings once told me you should call it the reality of the number field. It's the proportion of the primes which are real. Or not the primes, the embeddings, which are real. And notice that the type space here is kind of a weird object. It's the set of rational numbers between 0 and 1. And what about the critical invariant, this quality, the notion of equality? Well, again here, if we want to think naturally just as number theorists, we would take the root discriminant or the log of the root discriminant as the quality. But then remember that the game is a little bit different. Then we would be looking for the quality to stay small. And so that's why I've taken the reciprocal of that. The reciprocal logarithmic root discriminant is the degree of the field divided by the log of the discriminant. And if you remember in the Sayre video, if you watched it, he talks about how the degree is acting like the number of points because the infinite places are acting like the points. The infinite places of the number field are acting like the points of degree 1 on the curve. So with this setup, then we have the following upper bound for the asymptotic envelope. It's assuming that the GRH, then the asymptotic envelope is less than or equal to 1 over log of 8 pi plus gamma plus pi over 2 times t, this reality. This might look a little bit weird to people. That's just because I've normalized things by taking the t here is the number of real places divided by n. And the star is to remind us this is assuming GRH. So there's an unconditional bound also, but it's much worse. It's like log of 4 pi plus gamma, and the constant in front of t over 2 is also not as good. So what about lower bounds? So to find lower bounds, what does it mean? It means to find a sequence of number fields whose root discriminants stay small. That's the way I usually think about it. And as I said before, the only way we know for number fields is to find towers of number fields that are either unramified or ramified at a finite number of places but only tamely. Or you can have wild ramification also, but the depth of the ramification has to stay bounded. So as long as I call it shallow ramification, as long as the ramification is shallow and it's at finitely many places, the root discriminant will stay bounded. The trouble is you don't know how to find such things except for one tool. The only tool we have is the theorem of Golod and Shafarevich, which was really the start of Sayre's journey towards his 1985 course. And so using the Golod-Shafarevich theorem, Martinet wrote this beautiful paper in Invenciones in 78, where he showed that if you take Q zeta 11, the maximal real subfield of that, and you adjoin the square root of negative 46, that field of degree 10 has an infinite unramified class field tower, which means when you go to its Hilbert class field, the tower doesn't stop. That means it has non-trivial class group. When you go to its Hilbert class field and so on, the tower always goes up. And so you get an infinite sequence of number fields with exactly the same root discriminant. And the root discriminant there is 92.368, something like that. So, and that's a totally complex, all of them are totally complex. For totally real fields, he had to work a little harder, and the root discriminant was around 1060, 1059.6 is what I have. So together with Christian Mayer, around 2000 or so, we came up with some new ideas for how to try to beat Martinet's records. And we were able to do it, and we reduced those numbers in red. So in red, this was hard to read, and I didn't have time to make a table. So you can see the sequence of improvements. Basically, it goes from 92 to 82, and the current record, as far as I know, is from a recent paper with Ravi Ramakrishna and Christian Mayer, is 78.5. And on the total real side, we were also able to improve it to 857. It's hard to know how how to evaluate how big a jump this is. We just kind of measure it as a percentage, but it's still very, very far away from the ideal world where the GRH bounds would tell you the truth. Just like the Riemann hypothesis is known for curves over finite fields, and so that's why you might want to hope that A of Q, we know that A of P squared, that A of Q for Q being a square is exactly square root of Q minus 1, but I think it's more complicated than that. Anyway, you can see we're on the totally complex number, for example, it's 78.5 versus 44.7. So we still have a ways to go. And these improvements from the paper with Ravi and Christian is based on a new technique we call cutting of towers. And if there's time, I'll try to come back to that. So I wanted to talk about graphs a little bit because I've always felt that the story of Ramanujan graphs was a beautiful story that it had the same feeling to me as looking for curves with many points. And so by creating this stupid little abstract machinery of contexts and so on, I amused myself by putting it in the same machinery. And so I just want to quickly tell that story because I would like to encourage, I don't know if there's a direct relation between Ramanujan graphs and curves, but sometimes we can steal ideas from unexpected places. So let me tell this story also. So the objects are regular graphs. And so these are connected graphs where the number of edges coming out of each vertex is constant for the graph. So the type of the graph is just going to be the regularity index, the number of edges at each vertex. And the set of types, I'm going to assume that regularity is at least 3. It's not very much fun when the regularity is smaller than that. And the quality is something called the spectral gap of the graph. So let me talk a little bit about what that is. So the graph has an adjacency matrix, which is counts the ij entry counts the number of edges from the ith vertex to the jth vertex. So that's a real symmetric n by n matrix. When you compute its eigenvalues and write them in order, the graph being regular gives you that t is one of the eigenvalues, it's the top eigenvalue, and it's being connected gives you minus t. And so you have a sequence of numbers between negative t and t, which are the eigenvalues. And the really critical thing turns out to be the gap between the top eigenvalue and the next eigenvalue after that. So that's called a spectral gap t minus lambda of g, where lambda is the first eigenvalue. Well, the second eigenvalue, but the first one after the obvious one. And this measure of the goodness of a graph is algebraic and therefore good to play with. We have some tools to know what to do. But the reason why, the practical reason why people are interested in these kinds of graphs is, uh, I think it's called the Cheeger constant or the expansion ratio. But the two things are very closely related. So it suffices to study asymptotically good families for this quality function. They turn out to be the same. They're asymptotically good for this, um, um, if and only if they're good for the other goodness. And these graphs have lots of applications in all kinds of non-mathematical places, as well as within mathematics, coding theory, and cryptography. And this is one place where there's been a lot of progress in the last decade, which I'll try to describe. And it's also one place where the latest progress um, creates asymptotically good objects, beautiful ones, but without the use of automorphic forms. So here's the sequence of things to know. So there's a theorem of Alon-Bopana, which says the asymptotic envelope function for the spectral gap is bounded by t minus 2 times the square root of t minus 1. But most people probably notice as as an inequality in the other direction for lambda, for the first eigenvalue. And a connected graph is called T Ramanujan if its spectral gap is bigger than that, bigger than or equal to. So if you can find a family of T Ramanujan graphs, that means you found an optimal family. And the amazing thing is that Lubotsky, Phillips, and Sarnak discovered, I think it was 1988, was that when t minus 1 is a prime, they exist. And they come from the same place as everything else does, the modular curves. And that's why they're called Ramanujan, because Sarnak insisted that he wanted to call them Ramanujan because it was related to Ramanujan conjecture for automorphic forms. Now, the thing that's happened is over the last, I think it was 6 years ago, maybe a little longer, that Marcus, Spielman, and Srivastava, they've now shown that t minus 1 being a prime power, it doesn't matter. T can be any number. They can construct for you Ramanujan graphs for all t. And it's a really beautiful work, and I think there's lots of great ideas there. I don't know that they're directly relate to graph theory, to coding theory or curves, but I did want to point it out as really beautiful mathematics. So back to number fields. I I just realized today when I was finishing these notes that so I don't know too many papers where the title of the paper is a question. And Sayre referred to it in his interview that that he said Manin was very provocative. He said, "What is the maximal number of points on a curve over f2?" And he said that the fact that he said f2 was critical because it makes it feel more concrete. So it's not fq. Q is a parameter, but over f2 it feels like my interpretation of what he was saying was it feels like a question I should be able to answer. So these details are small, but together they add up to things. And so I found it interesting that Ihara, I know that Swassman likes this paper because the paper with Vladutz that I mentioned before is just very natural extension of it. The Ihara titled this paper, "How many primes decompose completely in an infinite unramified extension of global fields?" So again, it's a direct question. Give me the answer. 5, 7, 0? Usually the answer is 0. But he also demonstrated that you can make the answer anything you want. You can make the answer at least whatever you want, because you switch from working with the class group to working with the quotient of the class group. You can force things to split and still have an infinite extension. But it was a question that he asked, which was, can you have an infinite unramified extension of global fields in which infinitely many primes of the base split completely? And Christian and Ravi and I were delighted that we were able to answer this question recently. And so I just will put up the theorem. The statement of this theorem might be a little bit surprising also. So suppose K is a number field of signature R1, R2, so R1 real embeddings and R2 pairs of complex ones. And suppose the P rank of the ideal class group is strictly bigger than 2 plus 2 times the square root of the unit rank plus 1, R1 plus R2 plus 1. So usually the criterion says if it's bigger than or equal to this number, then the tower is infinite. That's the translation of the Golod-Shafrevich criterion in this setting. But when the P rank of the ideal class group is strictly bigger, what we were able to show is that there's some subtower inside the infinite tower where for every prime, the Frobenius elements are all of finite order. So every prime almost splits completely. It splits completely after a finite base change. And now the second theorem, which answers Yahara's question, is that, again, as long as the P rank of the class group is a little bit bigger than the Golod-Shafrevich bound, then there's a subtower which has infinitely many primes splitting completely. Now, I just want to say it occurred to me that let me just, I don't have time for a proof, but I just want to, there's just a lot of words that won't, this is just an invitation for you to go look at the paper, but don't worry about reading this, just listen to what I'm saying. So there's a Golod-Shafrevich polynomial that's, it's 1 minus dt plus rt squared, where d is the number of generators of the group and r is the number of relations. This is for any pro-P group that's finitely presented. But and usually people use that. And if this polynomial has a 0 in the unit interval, then it shows, or not a 0, but has a negative value in the unit interval, then the group is infinite. That's the original theorem. But its generalization, which was done by many people, starting with Winberg and Gaschutz and many others, Koch, is that you can take a presentation of your group and you can in fact make an infinite series because you can have infinitely many relations. So it's no longer a finite presentation, but it's a finitely presentable group. And you can form the same kind of series. And if that series has a negative value, then your group is still infinite. That result still holds. And so the simple idea that we had was just to take Frobenius elements of the primes and take them to sufficiently high powers and kill off, we have the big group, which is infinite, but then we quotient out, we cut it by these high powers of Frobenius. I always thought it was weird that it's called Frobenius, yeah. Anyway, in that way, you cut the tower stays infinite, but primes, the Frobenius have finite order. And then you have to refine that a little bit to prove the second theorem. The point I want to make is that we presented it just for number fields in our paper, but the proof works exactly the same for function fields. And so that means you're getting lots of points because you have infinitely many primes that are splitting completely. But it remains to be seen whether by playing with this, you can actually say anything about curves with many points asymptotically. Whether it has any effect on A of Q, I don't know, but I just thought I would explicitly issue an invitation for people to try to see if it helps with A of Q. I can't believe I finished exactly on time. So all I have left to say is merci.
Do we have questions, please?
Maybe I can just jump in for like a small comment about, I mean, your analogy with the graphs, and you said that, I mean, it was not clear. I mean, if it was, I mean, it seems that for me, the graph that Marc Perret and Emmanuel Eloin introduced, like for analyzing recursive towers, it is also a regular graph. And in order to analyze when, I mean, a tower is good, they are also comparing value of the spectrum of the adjacency matrix, right? Maybe some people could say more about that, but it looked a bit like there is a relation somehow.
Well, Christophe, that would be fantastic. That's exactly the kind of thing I was hoping that people who are more familiar with recursive towers and other ways of estimating A of Q would be able to find a relation.
Well,
so maybe I can add a little bit here. So in fact, this graph was already used by Elkies to figure out modularity of some of the towers. And I also used it to study some properties of graphs. And after that, the study was taken further by Perrin and Hedouin. But if you compute this graph for the using a modular polynomial, you get a Ramanujan graph. It's the Brandt graph. It's known that you can produce Ramanujan graphs like that. So,
that's wonderful.
Yeah.
Thank you, Peter.
Yeah, welcome.
Other questions, remarks? If not, I have two remarks. One historical, that when Margulis wrote his paper on Ramanujan graphs, before even he wrote it down, he spoke about it at a seminar. And he said that the idea came to him while reading our papers on curves over finite fields and codes. So for him, it was morally related. So that's one point. And another point is, since Farshid introduced that general formalism, it makes me think of quite another approach, which was for many years my dream, never fulfilled. That is that suppose that instead of asymptotically exact families of objects, we consider only towers, be that of finite fields, of curves over finite fields or of number fields, or there are analogs for codes for lattices, sphere packings, and so on. So let us restrict to towers, and then we have, for each tower, we have an infinite object, which is the projective limit of the tower for curves, or in the other direction, just the union of fields in the tower. And in fact, the invariance, what we do for, be that for codes, for curves, for anything, we work on a finite level. We work for a concrete curve. We find out the number of points, the genus, and so on. And then we go to infinity. Can we, instead of that, consider the projective limit of curves, the infinite object? And this limit should be a parameter of that infinite object. And can we write out that parameter by integrating over something or in some other way without descending to a finite level. So to work not with curves, but with pro-finite curves or infinite degree algebraic number fields. If someone could think how to put the question there, not speaking of how to answer them, I will be happy. And just as Farshid told us, for me, all these objects are very much related to one another, and the questions look quite similar.
I just have a comment that the only place I know where someone has tried to do what you're saying is in your paper with Fladutz, where you talk about these projective limits and you try to attach invariance to them and try to treat them as much as possible like number fields. I completely agree with you that if we're able to do that in a meaningful way, to try to carry over standard results from finite algebraic number fields to those fields, it has the potential of being extremely useful for a lot of these questions. So I guess I'm just saying I've always been scared to go there, but I hope that people pursue the idea. Like, could we have a class number formula for such fields, for example?
Yes, since we have infinite zeta functions, their properties are not so good as on the finite level. We can hope to have some relics of the functional equation and things like that. But directly that doesn't work. Directly we tried. So we need new ideas.
I think we need to get some physicists interested, because they're into this like renormalization, like they're not, this doesn't converge, who cares? I'm just going to compute with it. And throw away these terms and these terms, and these two are the good ones to keep, the kind of stuff that we're not good at doing sometimes because we're too rigorous.
We have an online seminar with German physicists, which is called Number Theory and Mathematical Physics. So it started this year. So maybe at some point, for the moment, we try to understand each other. It doesn't go very smoothly. But maybe at some point, it will converge. So.
Well, I just want to thank the organizers again. The format and everything about Zulip I find really useful to, like, I don't have time, but I hope to be able to come back and read all the conversations that are going on. This was my first experience doing math of any, because I have not been teaching either. It's the first time I've done math remotely. And there's something really nice about being able to connect with all of you, even though it's not as good as in person. The fact that we can do it all from our own homes is, I think it has some really good consequences for the future.
Okay, thank you again, Farshid. And we'll resume in 7 minutes.